Hey everyone, welcome back to Everything is Relative with me, Mr. K. Today we're going to be looking at more Papa Cambridge topical past paper questions, and this time on the topic of alternating currents, questions 332 to 337 for Cambridge A-level physics. As always, I'll leave a link in the description to these questions where you can use them to download them and use them to prepare for your exams, and then watch my videos. And if you need some guidance, then hopefully these videos will help guide you to the correct solutions. Now, as far as the Papa Cambridge questions go, I think this is the last topic that I need to cover, but there's still medical physics and cosmology that's outstanding, and so I'll put some questions together on my own on those topics and then share them with you and go over the solutions for those as well. But in this case, we're going to look at those questions of alternating currents that we didn't cover the last time. And these questions are going to look at mostly the half wave and full wave rectification for alternating currents, and how a capacitor can be used for smoothing as well. So as always, the first question, I'm going to write the question number down since it's blurry, is 332. And this is subject code 9702, which is A-level physics. This is from the March 2021 exam. It's question paper 4, variant 2, and question number 10 from that paper. We are told that the output potential difference of an alternating power supply is given by 320 sine 100 pi times t, where V is the potential difference in volts and t is the time in seconds. And we want to find the root mean square potential difference of the power supply. Well, the first thing we can do is write this equation in its general form. V is equal to the peak voltage V0 sine of omega t. So you can immediately see that what is outside the sine is the peak voltage V0, and what is next to the time inside the sine is the value for the angular frequency omega. So this makes our life a lot easier. So to find the root mean square potential difference of the power supply, we know that the RMS voltage is the peak voltage V0 divided by the square root of 2. This is 320 volts, which we can read off from the equation, divided by the square root of 2, which gives me 226 volts, to two significant figures, 230 volts. And so that's quite easy once we know the general form of the equation and link it back to what we're given. Next, we want to find the period of the output. And I don't know the period just by looking at the equation, but what I can see is that omega is 100 pi. I can't tell the period, but I can tell what the angular frequency is. And what I know is that the period is related to the angular frequency by 2 pi over omega. So that's 2 pi over 100 pi, and that simply becomes 2 over 100, which is 0.02 seconds. And so the period for this alternating voltage is 0.02 seconds. So quite straightforward once we know the general form of the equation. We're then told that the power supply is connected to resistor R and a diode in the circuit shown. We have a single diode, and they ask us to state the name of the type of rectification produced by the diode. Now remember, when we have a single diode, we lose every half cycle because the current is allowed to flow through the diode in the case where the upper terminal is positive and the bottom terminal is negative. But in the next half cycle, when the terminals swap polarities, then the current cannot flow through the diode and nothing happens. So this type of rectification is called half-wave rectification, which you should be mastering right about now, if you're not already. So this is called half-wave rectification. Remember, we have half-wave and full-wave, and this is a single diode, so it's a half-wave rectifier. We are then told that on the figure of 10.2, to sketch the variation with time t of the potential difference VR across R from time t is equal to 0 to t equal to 40 milliseconds. And so I need to plot a graph of what the voltage is going to look like with time. Now I know the voltage is going to be some sort of sinusoidal function, but I also know that there's a diode in the circuit. So the period I know is 0.02 seconds, and I can write the period down here as 20 milliseconds since my time axis is given in milliseconds. And the peak voltage we were actually given, well, indirectly given, to be 320 volts. If I know the period and I know the peak value, remember we can draw or sketch what the sine curve is going to look like. And so I first need to find 320. 320 is going to be here, and I'm going to plot 10 milliseconds and 320 volts. Why is that? Because after 20 milliseconds, what I have is the entire cycle that's occurring. So actually my time period here is 20 milliseconds, so the first peak is going to happen at 5 milliseconds. The sinusoidal curve is going to cut the x-axis at 10 milliseconds. We're then going to have another peak at minus 320 volts after 15 milliseconds, and then one complete cycle at 20. And then the pattern will repeat itself. But we have to be very careful that something else is going to happen that we have to take care of, because we have a diode in the circuit. So it's not a simple alternating current. So what I have is the first 10 milliseconds. I'm going to take the positive side as that which allows the current to flow. So my voltage is positive, and it's a half a sine cycle. And what I have then is that the second half of my cycle is negative, and that completes my one cycle. Then I have the polarity of the AC power supply changing again, and another positive half cycle. And then the polarity changing once again and the voltage becoming negative, and I have another half cycle. Now you're probably wondering why I've drawn dotted lines. Remember, I have a diode here. So positive current is allowed, but negative current is not allowed. So current is allowed in one direction, so potential difference can also be only in one direction. So every half cycle is being erased. This is why we call it half wave rectification. So I'm actually not going to have anything. Well, I've chosen positive. I don't have to choose positive. I can choose either positive or negative for my waves. But between 10 and 20 milliseconds, and then again 30 and 40 milliseconds, the potential difference is zero. We are removing those half waves. And so this is what the graph is going to look like. The period is still 20 milliseconds, but all we see is half the cycle. So we only see the voltage for 10 of those 20 milliseconds. So this is the big issue, obviously, with half wave rectification. And so remember that this would look very different if this was full wave rectification. And you need to be able to draw what these graphs would look like. So use the period, use the peak values, and then determine when the current or the voltage will be zero and when it will be actually the half wave visible. And so that was a 3-mark question that required you to understand what the diode is doing in the circuit. The last sub-question says, on figure 10.1, draw the symbol for a component that may be connected to produce the smoothing of VR. So this value for the potential against time is obviously fluctuating, but if we wanted to smooth this out, what could we do? Well, we know that for smoothing we can add a capacitor. And how do you add the capacitor? You have to make sure that you add the capacitor in parallel with the resistor in order that it charges and then charges when current is flowing through the circuit, and then discharges when the diode prevents current flowing through the circuit. And so we smooth the potential difference across R. And so we have none of those periods where the voltage across the resistor is zero. It may be low, but at least it's getting something from the capacitor. And so this question worth 8 marks is one on half wave rectification. Like I said, you need to be as comfortable with half wave rectification as you are with full wave rectification. The next question is number 333. And this comes from the summer 2019 exam. Summer being May, June 2019. And this is question paper 4, variant 1, and question number 10 from that paper. We're told that a bridge rectifier contains 4 diodes. The output of the rectifier is connected to a resistor R as shown in the figure. And the variation with time t of the input EMF to the rectifier is given by E equal to 15 cosine 210t. Again, we can write this in our general form. EMF is E naught, the peak EMF cosine omega t. T is measured in seconds and E in volts. And the variation with time t of the potential difference V across the resistor is shown in figure 10.2. So here we have what full wave rectification looks like. And you can see that instead of losing the negative half cycles, they are flipped over and they become positive. So we have more current more often. And they didn't really draw what the bridge rectifier looks like with the diodes, but they just said it's somewhere inside there. And this is what the eventual potential difference across the resistor would look like. And they ask us to first find the maximum potential difference Vmax across the resistor. Well, Vmax will simply be the maximum EMF across the circuit. So Vmax is equal to E naught, which we can read off from the expression, is 15 volts, since E is 15 cosine omega t. And so this maximum potential difference across the resistor is 15 volts. Now this is a fairly short question. They didn't expect you to draw or sketch or any of that. The next sub-question says the time interval, we want to determine the time interval to 2 significant figures between time t1 and t2. So we're given this graph and we're told that we need to find the time between t1 and t2, and we're given very little other information. But what I can see is that if the first loop here was originally a positive, then the second loop would have been negative. We just flipped it over the horizontal axis because we've rectified it. And the same would happen to the loop before T2. So what I'm seeing is 1 complete cycle and 2 complete cycles. 2 complete wavelengths, if you will, between T1 and T2. So 2 complete cycles happen in the time between T1 and T2. What this means is that what I want to find, which is T2 minus T1, the time interval between those 2 times, is actually 2 periods. The time it takes for 2 cycles to occur. And this is 2 times period is 2 pi over omega, which is 4 pi divided by the angular frequency omega, which we can read from the expression cosine 210 times t, which means omega is 210 radians per second. And this gives me a time between T2 and T1 of 0.0598 seconds, or again to 2 significant figures, 0.060 seconds. And so that's the time, that's 2 periods, 0.06 seconds. And if you were asked for the period, you would then say then it's obviously 0.03 seconds. And so you need to be able to understand, okay, there's actually 2 cycles between T1 and T2, but the negative half cycles have been flipped and made positive because of the rectification. We've turned the AC into DC. So not a very long question. That was altogether worth 4 marks. So that possibly means that there could be multiple questions that have alternating currents in them, or a very long question on magnetic fields or whatever. So 4 marks, not very long and not overly difficult. The next question is number 335, and this comes from the winter 2019 exam. That's October and November 2019. Comes from question paper 4, variant 1, and it was question number 10 in that paper. We are shown a bridge rectifier using 4 ideal diodes, as shown in the figure, and the sinusoidal alternating electromotive force, or EMF, applied between points A and B has a root mean square value of 7 volts. We are asked first to circle the diodes that conduct when B is positive with respect to point A. And we are obviously going to show this on the figure, on figure 10.1. Now this looks a little different to the bridge rectifiers that we are usually shown, but it actually works in the very same way. It's just a different way to draw it. Now if B is positive and A obviously is negative, then how do we know which of these diodes will conduct? Well, I just need to follow the path, right? Current will leave B and will attempt to go back to A. Now it can't go into the left branch because it'll be opposing the diode. So it follows the diode on the right, passes through this diode. It can't move up because it'll be against that diode. It'll move down and move from right to left across the resistor. It'll then move up. Now it's not going to branch off through the first diode here because that will just take it back to B. It means it has infinite energy. It's just going to be continuously moving from positive to positive terminal, which wouldn't happen. It's seeking the negative terminal. So it's going to move up and then through the next diode and back to the negative terminal, terminal A. And so when B is positive, the bottom right diode conducts and the top left diode conducts. So for the first half cycle, we have to circle the bottom right and the top left diodes. And so whenever you have to do a question like this, always a good suggestion would be to draw positive and negative terminals and then sketch your direction of current on the graph itself, on the circuit diagram itself, so that you can see which diodes will be conducting. The next question, A2, says calculate the maximum potential difference across the resistor. Well, this is quite easy. We're told what the RMS value is, so the maximum voltage is the square root of 2 times this RMS value. Are you trying to trick us? Because this is kind of fairly straightforward, but then again it is 1 mark, so it kind of makes sense. I don't want to give too much away. And this is the square root of 2 times 7 volts. Put this into a calculator and what you get is 9.9 volts being the maximum potential difference across the resistor. Now, we aren't done with this question just yet. We are told that a capacitor is connected into the circuit to produce smoothing of the potential difference across the resistor R, and the variation with time t of the potential difference V across the resistor is shown in figure 10.2. And we're also given the magnitude of the ripple in this diagram. Now we're told on figure 10.1 to draw the symbol for a capacitor that is connected so as to produce smoothing. So we need to go back to figure 10.1 and draw the capacitor as it would be to give us smoothing. And always we draw the capacitor parallel to the resistor. And this capacitor will provide the smoothing. So when the current is changing direction, then we can have the capacitor allowing the current to, or when the current is dropping rather, we can allow the capacitor to discharge across the resistor and smooth the potential difference to make it more like a traditional DC. For B2, we are asked to state the effect, if any, on the magnitude of the ripple on V when separately, firstly, a capacitor of larger capacitance is used. Well, the first thing I'm going to say is that the ripple depends purely on the time constant, which we sometimes call tau, the Greek letter tau. And this time constant is R times C, the magnitude of the resistance times the magnitude of the capacitance. If I have a larger time constant, I reduce the ripple because the capacitor decays much slower. And so I have a high value of the time constant. If I have a low value of the time constant, the capacitance decreases rapidly. So if I want less ripple, I need a high value of the time constant, which means I need a high capacitance. So what happens to the ripple? The ripple itself decreases because I'm using a capacitor that can actually provide current for a much longer time. So I will say that the ripple decreases. Now separately, part 2 says what happens if I use a resistor R with a smaller resistance. Well, if I use a smaller resistance, then the time constant decreases. And if the time constant decreases, then I have a ripple that's going to be larger. So the distance, the ripple would be the distance from the peak to the lowest point, and it's a higher value. So I will have a ripple that increases. So I have a bigger value of the ripple because the time constant decreases. So essentially, if you wanted to look more DC, you would have a higher time constant. May not always be the case, but generally you would want to reduce the ripple and so you would have a large value of capacitance and a large resistance if possible. So that question contained quite a few parts about the rectification process. Altogether, it was worth 5 marks, but it did require knowledge of different aspects of the rectification process and smoothing as well, which again, like I say, you need to know and understand and be comfortable answering questions on. Now the next question, which is the last for this video, is number 337. Once again, it's subject code 9702. This comes from the winter 2017 exam. Question paper 4, variant 2, and this is question number 11 from that paper. Now, we are told that the circuit for a full-wave rectifier using 4 ideal diodes is shown in figure 11.1, and this looks something more like what we are akin to seeing for the bridge rectifier. A resistor R is connected across the output AB of the rectifier, and we are asked on figure 11.1 to draw a circle around any diodes that conduct when terminal X is positive and Y is negative. So like we did before, X is positive, Y is negative. I need to circle the 2 diodes that are going to conduct for this first half cycle. So I'm going to again trace the current. The current goes from X from positive to negative. As it enters the bridge, it's going to turn left because it can't move to the diode on the right. It's then going to come out of the bridge and then pass through the resistor from the bottom to the top, past point A, and now it's going to have to choose. So it's not going to go back the way it came, because again, that's going to be a loop that's never ending, infinite energy. So it's now going to go through this diode on the bottom right, and then it's going to find its way back to the negative terminal Y. And so as I can see in this half cycle, the top left diode and the bottom right diode are the ones that conduct when X is positive and Y is negative. So always trace the current. It makes it easier than having to guess and try and do it in your mind, and also reduces the chance of making an error. We're then told to label the positive and the negative terminals of the output AB. Be careful, not of XY, but the positive and negative terminals of the output AB. Now it turns out that if Y becomes positive and X becomes negative, that the current will still flow in the same direction across R. Hence we are turning AC to DC. And the current flows from positive to negative. So that means the positive end will be side B, and the negative end would be side A, because current is flowing from positive to negative through the resistor, from bottom to top. So the bottom of the resistor is positive and the top of the resistor is negative. Or you could have just put the labels on B and A themselves. But essentially that's the direction of current that flows through the resistor. It'll always be in the same direction because that's what rectification does. Now part B says the variation with time t of the potential difference V across the input XY is given by V equal to 5.6 sine 380t. And we immediately know this is V is equal to V naught sine omega t. V is measured in volts and t is measured in seconds. Now the variation with time t of the rectified potential difference across the resistor is shown in figure 11.2. And we are told to use the expression for the input potential difference, V or otherwise, to determine the root mean square potential difference of the input. Again, 1 mark. Why? Because V naught is already given. So the RMS voltage is the peak voltage divided by root 2. The peak voltage, as we can read from the expression, is 5.6. 5.6 over the square root of 2 is 3.96 volts. Or to 2 significant figures, 4 volts. And so quite straightforward, and hence it was just worth 1 mark. But the next sub-question says, determine the number of times per second that the rectified potential difference at the output reaches a peak value. The number of times per second that the rectified potential difference at the output reaches a peak value. Now, the number of times, now the peak is reached, if you look at the peak here, the peak is reached twice every period. So in one cycle, it happens twice. This peak is reached once, and the negative peak is shifted above the horizontal axis. And so for every period, I have two peaks occurring. And so what this means is the number of times that the potential difference reaches its peak value every second is equal to twice the frequency. The number of times per second, frequency is number of times per second. It's 2 times f, which is 2 times omega over 2 pi, since frequency f is omega over 2 pi. So this is simply the angular frequency omega divided by pi, which is 380 radians per second, which we got from our expression above, divided by pi. And so this is 121 times every second that the potential difference will reach a peak value. And that's 120. So the peak value happens twice every cycle. And so the frequency multiplied by 2 will tell me how many times we have a peak occurring every second. And so it happens to be 120. We're then told that a capacitor is now connected between the terminals A, B of the output, and the capacitor reduces the variation, reduces the ripple in the output to 1.6 volts. And on figure 11.2, we want to sketch the variation with time t of the smooth output voltage for time t1 to time t2. So between t1 and t2, we want to sketch the variation of the voltage with time. And it's a 4-mark question, so quite a lot of work is to go into this for sketching. So what's the first thing I need to do here? Well, the first thing I need to do is I know that the smoothing reduces the voltage by 1.6 volts. And my peak voltage is 5.6. 5.6 minus 1.6 is 4, which means my minimum voltage when I introduce the capacitor for the smoothing is going to be 4 volts. And I need to start at T1 and I need to end at T2. So how does smoothing occur? Well, we don't allow the peak or the hill to go all the way down because we lose too much of current. So the capacitor kicks in when the current begins to drop. Instead of allowing it to drop rapidly, it allows it to drop less rapidly. And so going from one hill, from the peak of one hill to the ascent of the other, I have a curved line that decreases like a capacitor would exponentially until it reaches the second hill, and then the current in the circuit overtakes the capacitor and takes over again. And then as it reaches the peak and is about to drop, the capacitor kicks in and the same pattern happens. It drops 1.6 volts to its minimum value. Again, when you have a pencil, you can draw this a lot neater than I am, but you can see the pattern here. It goes to its maximum, the capacitor kicks in and provides current at an exponentially decreasing rate until it reaches a point where the current in the circuit is greater than the current coming from the capacitor, which means the capacitor can then charge, and the potential difference that is across the resistor increases sinusoidally. And so I'm specifically asked to go between T1 and T2, and this is what it would look like. So you need to make sure that there's a curve because the capacitance decreases exponentially, which is a curved shape. It needs to start on the peak and needs to drop to 1.6 volts, which must be on the second line. So it must be on the upward rise of the second hill. And the pattern must be repeated, must be between T1 and T2. And so you can see that this is what a smooth output looks like. A lot better than having those deep valleys in between. And so the more I increase the capacitance, the less of the ripple I will have. Lower and lower ripple means the graph will look more like a straight line. And so that was not that much of work, but you need to know how to make this graph look in order for it to be completely correct. And so that's what smoothing looks like. So make sure if that doesn't make sense that you go back and understand the topic of smoothing after understanding rectification. Now the last question says we should suggest and explain the effect, if any, on the mean power dissipation in resistor R when the capacitor is connected between the terminals A, B. Now the power, the mean power, is proportional to V squared. The resistor is not changing. But what I can see is that the potential difference is increasing. The average potential difference is increasing. The mean potential difference is increasing. Why? Because I'm not going all the way down anymore. The capacitor is allowing the potential difference to stay higher for longer. It's not going down and coming all the way back up. It's smoothed. So since the potential difference is higher, what do you think that means for the power? So I'm going to say the mean potential difference increases, or you can say the root mean square potential difference, that's fine as well. The mean potential difference increases, so the mean power increases. And if you wrote the little note that I did in the side, the mathematical expression, that's perfectly fine as well. So since the mean potential difference increases, so too does the mean power. Obviously, we'd expect more power if we are going to take all these hills and valleys and turn them into a more smooth, more straight output, more like an actual DC output. So more potential difference means more mean power. And so that was the last question on the topic of alternating currents. And we covered most of the bases, if not all of the bases of alternating currents, and I hope that these videos were helpful. Like I said, there are no Papa Cambridge questions as far as I can see on the topics of medical physics and cosmology. So I'll be creating my own topical questions, and in my next video I will go over the solutions of those, and I'll attach those questions to the video description as well. So you can download, work with those questions, and then come back to my video to see how we can go about solving problems on medical physics, and I think more importantly astronomy, which is a lot less theoretical and can have a lot more mathematics and conceptual understanding, especially of things like quantum mechanics is required. So from me, Mr. K, that's all for now, and everything is relative. Please leave a like, comment, subscribe to the channel if you haven't, and I'll see you again next time.